So welcome. This is a worksheet based on proof by contradiction using mathematical induction topic. So what is the first question? Consider two positive integers k and k plus 1. Show that the difference of their squares is equal to the sum of the two integers. So difference of the squares k plus 1 whole square minus k square. So which is k square plus 2k plus 1 minus k square. What happens? K square and k square gets cancelled. So what do I get? 2k plus 1. I can write it as k plus 1. See, this is the sum of the two integers. K and k plus 1 sum is nothing but 2k plus 1. So it has been proved. So very easy question. Question number 2. Prove that the sum of three positive integers is divisible by 3. So let n plus 1 and n plus 2 are three positive integers. They are three positive integers for n belongs to z plus. Now n plus 1 plus n plus 2 equals to how much is that? 3n plus 3. So what can I write it as? 3 bracket n plus 1. So we can see that it is a multiple of 3. 3 times something is multiple of 3. That's going to be the answer. Question number 3. The product of three consecutive integers is increased by the middle integer. Prove that the resultant is a perfect cube. So what are the three positive integers? We take it as n minus 1, n and n plus 1. This will be the easiest way, where n belongs to z. Now what is he telling it out? The product of these three integers, n times n minus 1 times n plus 1 is nothing but what? N times n plus 1 times n minus 1 is nothing but n square minus 1, which is nothing but how much? N cube minus n. Now the product of these three integers is increased by the middle integer, so n cube minus n plus n. So it becomes n and n gets cancels, n cube, which is a perfect cube. That has to be proved. Question number 4. Show that 2n minus 1 whole cube then plus 2n plus 1 whole cube equals to 16n cube plus 2n. So a minus b whole cube formula is a cube minus 3a square b plus 3ab square minus b cube plus this part a plus b whole cube, a cube plus 3a square b plus 3ab square plus b cube. We are supposed to add these two. So 1 cube cancels, this and this gets cancels. So what am I going to get it out? 8n cube plus 8n cube is nothing but what? 16n cube plus this is going to be 6n plus 6n, 12n. So that is what he's asking us to prove it out. Hence or otherwise that prove that sum of the cubes of any two consecutive odd integers is always divisible by 4. So we know that 2n minus 1 and 2n plus 1 are consecutive odd integers. They are consecutive odd integers. The sum of them, just now we have cubes, sum of the cubes. So 2n minus 1 whole cube, 2n plus 1 whole cube is how much we have proved it as? 16n cube plus 12n. We have to prove that it is divisible by 4. So can I take 4 common? It becomes 4n cube plus 3n. Yes, it has been proved. We can still take 4n also common, but 4 is sufficient enough. Question number 5. Use induction to prove that. So first I have to form it out. Basis step. Left hand side n equals to 1. So what do I get? 1 square. Right hand side n equals to 1. 1 times 1 plus 1, 2 plus 1 upon 6, which is 1. Therefore, left hand side equals to right hand side. The statement is true for n equals to 1. What can I write? The statement is true for n equals to 1. So we can write as this as Sn. Sn is true for n equals to 1. Now, assumption. What is assumption? Let us assume that it is true for n equals to k plus and so on plus k square equals to k times k plus 1 times 2k plus 1 upon 6. Now the induction step. We have to prove that it is true for n equals to k plus 1. So 3 square plus and so on plus k plus 1 whole square. So should be equals to, when I simplify that, it should become, plug in k plus 1 in the right hand side also, k plus 1. K plus 1 plus 1 will become k plus 2. 2 times k plus 1 plus 1 will become 2k plus 3 upon 6. I have to prove this. So before term would have been k square. So what do? I write 1 square plus 2 square plus 3 square plus and so on plus k plus 1 whole square, and before term would have been k square. This entire substitution becomes k plus 1 k times k plus 1 times 2k plus 1 upon 6 plus k plus 1 whole square. Now 6 is missing, so multiply and divide by 6. Now I can take the common denominator as 6 and k plus 1 common. So what am I left over with? K times 2k plus 1 plus 6 times 1 more k plus 1. So what is that? K plus 1 times 2k square plus k plus 6k plus 6 upon 6. What does that becomes? K plus 1 times 2k square plus 7k plus 6 upon 6. We know that 2k square plus 7k plus 6 can be factorized into k plus 2 times 2k plus 3. Therefore, it is true for n equals to k plus 1. By conclusion, you can write that as it is true for n equals to 1 and n equals to k plus 1. By principle of mathematical induction, it is true for all values of n. Question number 6. Use the principle of mathematical induction to prove this one. So, let this statement is Sn. I take the left hand side. N equals to 1, it becomes 1 times 2 power 1, which is 2. Right hand side, plug in n equals to 1. 2 plus 1 minus 1 times 2 power 1 plus 1. 2 plus 0, which is 2. So we can see that left hand side equals to right hand side. Therefore, Sn is true for n equals to 1. Now, let us assume that it is true for n equals to k. 2 times 2 square plus 3 times 2 cube plus n times 2 power n equals to 2 plus, instead of n, what am I going to write? K. K times 2 power k equals to 2 plus k minus 1 times 2 power k plus 1. Now I have to prove that it is true for n equals to k plus 1. So, plus and so on plus k plus 1 times 2 per k plus 1. It has to be proved. What it has to be proved? It has to be proved as k plus 1 also in the right hand side. K plus 1 minus 1 times 2 per k plus 1 plus 1. So we shall try. So the before term would have been k times 2 per k. So what is this entire substitution can be written as? 2 plus k minus 1 times 2 per k plus 1 plus, what else is left over? K plus 1 times 2 per k plus 1. What can I do? 2 per k plus 1, 2 per k plus 1 can be common. So it is 2 plus 2 per k plus 1 common. What am I left over with? K minus 1 plus k plus 1. So what does that happens? 1 and 1 gets cancels. 2 plus 2 per k plus 1 times 2k, which is nothing but what? The same thing. 2 times, it's going to be the same answer. So once it is proved for n equals to k plus 1. By conclusion, we can write it as Sn is true for, what can I write over here? Let me write it out quickly. So what I can write as Sn is true for n equals to k and n equals to k plus 1. Hence, by mathematical induction, Sn holds for all n belongs to z plus. Next question, we have to prove this one by using mathematical induction. So now what am I going to do it at? I'm going to do the base case or basis case. Now if I plug in n equals to 1, it is r power 2. It becomes r power 2. Means basically nothing but what? Two terms. Sum to two terms on the left hand side. What is sum to two terms on the left hand side? 1 plus r. When I simplify that one also, n equals to 1 in the right hand side, I should be getting it out n equals to r 1 plus r. So 1 minus r square upon 1 minus r. So 1 plus r times 1 minus r divided by 1 minus r. 1 minus r, 1 minus r gets cancels, 1 plus r. So therefore sum to two terms is going to be nothing but how much? 1 plus r. So therefore it is true. Base case is true. Now let us assume that it is true for n equals to k. 1 plus r square plus and so on, r power k equals to 1 minus r to the power of k plus 1 upon 1 minus r. Now we have to prove that it is true for n equals to k plus 1. So 1 plus r square plus and so on plus r power k plus r power k plus 1. And what should be my final answer? My final answer should be looking like 1 minus r to the power of k plus 1 upon 1 minus r. This should be the final answer. So this entire thing can be written as 1 minus r power k plus 1 upon 1 minus r plus r power k plus 1. Then the denominator is 1 minus r is missing. So multiplying and dividing by 1 minus r. So what do I get from there? I move this one so that I get space for writing it out. So r minus 1 is the common denominator, or 1 minus r is a common denominator. So it becomes 1 minus r power k plus 1 minus or plus r power k plus 1. R power k plus 1 times minus r is r power k plus 2. We can clearly see that r power k plus 1, r power k plus 1 gets cancels. 1 minus r power k plus 2 upon 1 minus r. K plus 2 can be written as k plus 1 plus 1. So therefore it is true. So we can write it out again by mathematical induction. It is true for n belongs to z. Now question number 8. Prove by induction that root 3 is an irrational number. So let us assume that it is irrational number. Rational number means a upon b, which is in simplified form where you cannot simplify it further. So let us assume root 3 is rational. So what do I get it out? Root 3 equals to a upon b. Then squaring on both sides, 3 equals to a square upon b square. So a square equals to 3b square. It indicates what is that? A square is divisible by 3. A square is divisible by 3. If a square is divisible by 3 means a is also divisible by 3. A is divisible by 3 means let a equals to 3p. So plug in that one. 3p whole square equals to 3b square. So 9p square equals to 3b square. So b square equals to 3p square. Means b square is multiple of 3. B square is multiple of 3. Means b is multiple of 3. B is multiple of 3. Means b equals to maybe 3 cube. But what we have assumed root 3 was a upon b in the simplest form. We cannot simplify it further. But I got 3p upon 3q. So 3 can be simplified. So which is not possible. So therefore, what is this? Assumption is wrong. Assumption is wrong. And root 3 is irrational. Next, question number 9. The Fibonacci sequence is defined as follows. Prove by mathematical induction a1 square plus a2 square plus an square equals to an plus 1 where n belongs to z. So first base case n equals to 1. So a1 square equals to nothing but what? Which is 1 square, which is 1 from the left hand side. This is from left hand side. From the right hand side, a1 times a2, which is 1 times 1, which is again 1. So therefore Sn is straight. Let this be Sn. So Sn is true for n equals to 1. True for n equals to 1. Let us assume that it is true for n equals to k. So what does that becomes? A1 square plus A2 square plus and so on plus AK square equals to AK times AK plus 1. Now I have to prove that it is true for k plus 1. A1 square plus A2 square plus and so on plus AK plus 1 square should be equals to, what should I prove? I should prove it as AK plus 1, AK plus 2. Now this entire thing, before term would have been AK square. So this entire thing goes under the assumption. What was that assumption? AK times AK plus 1 plus AK plus 1 square. So what can I take common? AK plus 1 common. So what is left over? AK plus AK plus 1. So we got AK plus 1. That's nothing but what our Fibonacci sequence. What does it mean? If at all you add the two terms, you'll be getting the next term. So therefore it is nothing but what? That's a Fibonacci sequence, right? Because this question is all about Fibonacci sequence. 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 5 is 13. You add these two, you get this one. You add these two, you get this one. You add these two, you get this one. So k plus 1 will become k plus 2. So ak plus 1 times ak plus 2. I think so that is only asked us to prove. So by conclusion, we can prove that it is true for n belongs to z. So prove by contradiction that has no integer roots. So we will simplify that. Let n satisfy this one. So 3n cube minus 7n square plus 5 equals to 0. So what does it become? 3n cube plus 5 equals to 7n square. So we'll take the first case. Let n is odd. If n is odd, so what will happen? If n is odd, 3n cube will become odd number and 5 is also an odd number. Sum of two odd numbers is nothing but what? Even number. And n square, 7n square will become an odd number. So an even number cannot be equal to odd number. So the first case is not possible. Now the second case, if n is even, 3n cube will become even and 5 is odd number. So even number plus an odd number is going to be an odd number and 7n square is going to become an even number. So even number cannot be equals to odd number. So it is not possible. So what we have shown? We have shown that for n belongs to z, whether n is odd or even, the equation is not satisfied. The equation is not satisfied. Hence there is a contradiction. This is going to be the answer. So that completes this worksheet. See you in the next worksheet. Bye.